Hi, everyone. I'd like to welcome you to the last session of the day, which is a panel discussion. We have 4 very exciting panelists here, and I'm going to start by giving them each a chance to introduce themselves and say what their interest in P4 is. And then we have, of course, the questions from Pigeonhole that you guys have been voting on throughout the day, so we'll take turns answering those. And I guess it's still open, so if there's some other questions that come up, feel free to type them in, and they'll get projected up here. So, Mario?
Okay, thank you, Robert. My name is Mario Baldi. I work for Cisco Systems. I'm an architect for an XOS, which is the operating system that we have on our data center switches, the Nexus family switches, if you are familiar with them. So the reason why I got close to P4, and I'm relatively new to P4, is because I'm trying to look into how we can leverage it, as a vendor, or how our customers can possibly leverage it, and this is going to have impact on the operating system of our switches, and that's why I'm looking into it, to figure out what we need to do in our operating system to support a programmable data plane.
Thank you. Welcome.
Thanks.
Hi, I'm Anirudh Shivraman. I'm an assistant professor at NYU. My interest in research is broadly computer networks and more specifically router design. So I got interested in P4 as a grad student a couple of years ago when I realized that there wasn't any easy way to express new algorithms that ran inside the network, because you either had to use a really low-speed software router, or you had to go and convince a hardware vendor to put new algorithms in. And this was kind of frustrating because you couldn't ever evaluate things at sort of production speeds, so you would never even know if an algorithm was good or not. So that was sort of my interest in P4, and so my thesis work was roughly around this area of hardware and software for programmable routers, and that's how I got interested in P4.
Okay. Yeah, hi, I'm Anurag Agrawal. I'm working for Barefoot Networks as a chip architect there. So my views are biased. in a way, we developed the technology which is helping P4 to proliferate everywhere. I got to Barefoot 4 years back, so I'm pretty early on. I was in Juniper Networks before that, so I've been building routers or switch ASICs for a while, more than 15 plus years now. The thing which caught me when I talked to Nick and the few founders at that time is the notion of the things were evolving that time, having like SDN and a lot of other things which wanted the programmability in the network. And I saw this opportunity sitting with Nick, and I said, okay, this seems really exciting. Can I join? And that's where I started working with these guys. It's a pretty exciting journey for us to be here with you all and enabling all of you to work on P4.
Thank you.
Hi. Thanks, Robert, for the invite. My name is Dan Vucinic. I work at Western Digital Corporation. I'm running a research group in the research division. Our interest in P4, we are interested in all kinds of network, first of all, right? We are a storage maker. So if you think about it, all storage that we sell, essentially everything that we sell is attached to some kind of network. And unlike Anurag, we are quite unbiased in that we'll sell to whatever network you have out there. Our interest in P4 stems from several angles, right? From the more mundane to the more exotic. First, there's the proliferation of protocols for network access to storage, for instance, NVMe or Fabric, right? So we're always looking out for ways to accelerate these protocols and to make the storage accessible, lower latency and higher bandwidths. The second thing is that there's a lot of storage systems that work in software. And as Robert's students have shown recently, P4 is actually capable enough to move some of this functionality that we normally do in software, such as replication or consensus protocols, into the switch itself, right? So instead of running RAID as a software driver, you basically load it into the switch, and then it's completely transparent to you. Also things like fault tolerance and so on. So we're very excited about the possibility for innovating these new functions into the network that we normally do in software. And then the third is kind of a more exotic angle, which is actually how we came into this story. So my group is focusing on the non-volatile memory, the future non-volatile memories, such as resistive RAM and phase change memory. And these are kind of falling in between NAND flash and DRAM. And so if you think about NAND flash, all of it is connected to some sort of network, either through PCIe or through SAS or SATA. But DRAM, basically none of that is connected to a network. It's all sitting directly connected to the CPU. These new memories kind of fall in between, where they're sort of storage, but they could be used also as main memory, but a little bit slower. So these P4 switches are actually a very interesting story for us to see how we could disaggregate this memory and scale it out independently of compute. So we could attach compute to a network and then have a custom protocol that is doing coherence and consensus and all these nice features that we like to do be done in the switch itself, not in our custom ASIC. So that's where we come from.
Great, thank you. So let's get started with the questions. Currently, the highest voted question is, what are some application areas where P4 is likely or unlikely to succeed? Mario, do you want to start?
Well, yeah, this is also the most important question in general. Well, yeah, honestly, I obviously don't have an answer, but a clear answer, but I would think maybe one case could be when for the application it's important how data is forwarded, and it's not forwarded just based on the typical information we use for forwarding, which is layer 3 forwarding, because that's something that we do in very specific ways, in standard ways. But if we need to forward based on some application layer information, some according to information that's put in the packet, and this doesn't have a very, how can I say, of course not standardized, but also not solidified format. We are still working on it. We are changing it over time. Then we want to be able to adapt our
Do you mean
nodes.
Like application level protocols, or do you mean new transport protocols?
Yes.
Both.
Yeah, but I'm thinking more of application layer.
I see.
More than application layer protocols, forwarding packets using application layer information. So it might not be necessarily a protocol that has a way, that has gateways, but we want to be able to direct our packets based on some information that we find above layer 3 and 4. So, and it is not, it doesn't have a format that's for sure not gonna change for a long time. So we want to be able to adapt. Another case that comes into my mind is when we have end users that have proprietary, well, it was also mentioned, I think, in the first presentation today. If a user has proprietary protocols, of course, he cannot go to a switch vendor and ask them to implement those protocols. So that could be another case, although it's probably not such a common case.
Yeah. So Mario, you come from a networking company, but Dejan, you come from a pretty different company, a storage company. And so I think you might have a completely different perspective here. I mean, you already touched on some of these things.
Right, so I think there's two answers to this question, right? One is in the short term, you're going to get a very fervent audience from people who want to innovate in the protocols, right? Who don't want TCP. In the long term, what we would like to see, or what I would like to see is, we can discuss, what song this dog is going to sing, but there's more the point that the dog can't sing at all, right? So right now the switches can't do certain things at all. For instance, Paxos is a good example, right? But there are other ideas that we have in mind. So really what we'd like to see is that all the Ethernet switches deployed in a data center in 10 years from now have P4 or some kind of language like that running in them, right? So I don't know what event would precipitate that, but I think the storage scale-out and the storage functions are actually a very good candidate.
Onur, you coming from the more academic research background, what's sort of driving your research forward? Are there any interesting areas that you'd like to look at?
Yeah, so one thing that, I think is a big pain point with switches today is support for monitoring, troubleshooting, measurement, and so on. So, it's a fairly broad category, but, when things go wrong, there's very little support now to like really get deep into the switch and instrument like every packet, figure out what its queuing delay was, what the queue size was when the packet went in, what it was when it came out. And technologies like INT and more generally the ability to deeply instrument the switch when things go wrong, not necessarily in steady state when things are working okay, I think is hugely powerful. Like as a researcher, I do this all the time in simulation, right? Like, you can add all kinds of logging statements in simulation to understand exactly what is going wrong at every instant in time. But it would be really cool to have that kind of same capability in a production network. And I think for me at least, the ability to like, deeply understand what is going on at like packet to packet timescales without having to sort of tie your hands behind your back and infer it from the end host, which is partly what happens today. You sort of do these end-to-end measurements from different vantage points and try and fuse it together. So yeah, I guess measurement and troubleshooting is like one big application area that I think P4 can really help.
I see. So my own background is very much at the software level, and I really didn't think much about sort of, I always just assumed any software I could write could just run on the hardware. And then I was sort of surprised starting to interact with more hardware people that are designing these devices. I said, oh, I just want to have some, I'd just like to add some sort of, checksum or maybe expensive hash that we can securely encrypt all the packets going through. And they say, look at me like, are you crazy? Do you know how many gates that would take? And no, I have no idea how many gates that would take. I'm software. It looks like a for loop to me. So Anurag, with your background coming more from the hardware perspective, what do you think of this sort of software perspective of the types of applications that are appropriate to run on these devices?
That's a very broad question, what is appropriate to run. I think I don't want to limit the imagination here is that only it is for switches or it is for NIC. It's essentially P4 is a language to make the hardware do certain things. We try to build the hardware with a lot of flexibility in our Tofino chip, definitely, and going forward as well. The things like, I think today you guys did some cool application, just building a calculator in the switch. Means it's unthinkable as a hardware engineer for me that somebody could do that silly thing. But that's the idea we wanted to show that, okay, you could think in a completely different way. It's not just switching the packet from A to B or everywhere, but it's basically what can I do to this packet along the way. Means you can make a silly game of playing a tic-tac-toe on it, is that one guy saying cross, one guy saying, oh, and put the state in the switch. Yes, you can. That P4 allows you to do that. No other switch can do it, or no other devices can do without help of P4 or those kind of. So this means where it will be unlikely to do. I'm not sure. We believe it will evolve to do more into the areas like deep packet inspection if we stay in the networking domain. It will go further, encryption, decryption. Things will evolve along the way as all of us will try to use it in a different ways. Hardware is capable of doing a lot of things. There will be limitations. We are also learning from your experimentation and from academia and industry both ways. We are evolving those things. Like Robert was saying, they are doing CRC check. It's not cheap, but we try to build it in the hardware to allow that flexibility. Okay, you can add one more CRC or delete it or things like that. So the idea is that how much you can play with the packet. There will be an eventual limitations comes in the hardware. I don't believe that you can take a whole jumbo packet and modify every part of the packet from in to out. I don't believe you can see a tail of the packet and make it head. That may not be doable in a foreseeable future. I don't believe. It's not that we cannot do it eventually, but not in a few years. So I don't think so. It cannot evolve to do things which we haven't even thought of yet.
Robert, regarding what you were saying about resources, maybe another area where programmable chips, programmable ASICs can can bring really major changes where you need very high scale or where you are working with very constrained resources. And what I mean is today we build ASICs that have a ton of functionalities on them. And then every use case requires only a small subset of them. So of course, still we are able to put all of those functionalities on the chip and we use it, but maybe, and I'm not sure that this is going to be the case, but maybe vendors like Barefoot or others who will make programmable chips will prove that if you take a programmable chip and you create a P4 program that has only the features that a certain use case requires, finally, with the same number of gates, you might achieve much more scalability.
Yeah.
Just because if you make an ASIC, you're not going to make it tailored for that application, right? So maybe one area of deployment will be tailoring the data plane to just what's needed and consequently being able to run on a limited number of gates in resource-constrained environments, where you have power constraints or space constraints, or vice versa, given our capability of putting a certain number of gates on a chip, being able to run at very high scale, like very large number of ports or very high speed.
Oh, that's a great point. So let's move on to the next question, which I think is probably important to a lot of people here, is what tools do you actually think that we need for the P4 ecosystem?
Should I start?
Sure.
I think we need a NIC, right?
What?
We need a P4 NIC. So we have this switch that we're playing with, and it's great, but really what's limiting us right now is the NIC is the FPGA, right? So the scale at which we can, the bandwidth and the latency scale at which we're playing with right now is fairly poor compared to what the switch can do, right? So we get the flavor of what's possible, but before we have, until we have an ASIC NIC that you can program custom packet formats and do some processing on them, I think that would be I don't know if that counts as a tool or is there a major hardware leap, right?
Sure.
From my side, it's essentially a verification kind of tools where you can formally verify or in a way that is this program working program or does it have bugs or do we need to evolve something. Also the capability of this program, can it compile on different targets? So those kind of early indications will help people to build the programs which are a lot more portable than just, okay, it works on Barefoot, but cannot be portable to anything else. It won't be helpful.
So yeah, I guess at some level the tools you need for the P4 ecosystem are similar to the tools you'd need for any language targeting any piece of hardware. Like you'd need a compiler, you'd need a debugger, you'd need hopefully an IDE and so on. The thing that makes the P4 style targets, especially the switch targets, a little more interesting to me is that there's this sort of cliff effect where your program either runs full blast or it doesn't fit at all and it doesn't run at all. So unlike x86 where a more complicated program just takes longer to run, here it's all or nothing. Now making that clear to the user turns out to be quite painful because they make minor changes to their program, suddenly it doesn't fit, right? It's just slightly beyond the capabilities of the ALUs on the switch, right? So I think better diagnostics to the end user, either through the compiler, I guess in the short term you could just have tech support teams do this, but I think longer term, more sane diagnostics, especially when the program doesn't fit or doesn't compile for any number of reasons, like you're trying to do one too many manipulations on the packet headers, right? And it should be clear to the user that that's what was wrong.
So that's an interesting point, but do you have any thoughts on sort of this cliff that you mentioned? Do you have any thoughts on ways that we could approach that? Maybe like, I don't know, proposing a subset that would fit or modifications that might make it fit, or do you have any thoughts for directions we could push on that?
So my own experience with this, so I worked on this project to add stateful support to P4, both the hardware and software levels. The best answer I have is something similar to delta debugging, where you have a program that fits, a program that doesn't fit, and then you just keep trying to narrow down the difference between the two. It's not particularly effective, but it kind of works, right? You just try and narrow down the difference to the point where you are satisfied with, okay, this subset of the program fit, this one didn't, and the difference is small enough, and maybe this difference was the cause of the problem, right? But automating that process and not having to sort of go through this tedious iterative process on the programmer side, I think would be really helpful.
Mario, do you have any thoughts?
Well, yeah, I mean, along these lines, I think another component that's missing is the equivalent of a linker that you have with regular software development, like supporting the capability of different actors writing different parts of a P4 program, because you know, there are several scenarios, and the current tools don't support it at all. But one of the scenarios I have in mind is, from a vendor's point of view, is a vendor might have his own data plane implementation, and the customer might want to add on top of it. So how do you handle that? I mean, obviously the vendor doesn't want to give its own P4 to the customer. Even if the vendor does the P4 to the customer, then if the customer, by making some modification, is going to change the behavior of the vendor's P4, the operating system is not going to support it anymore. So there are a number of problems there. And so if we had a way of defining clear interfaces and of compiling two different modules separately and then linking them together, that could be probably very useful, both in this scenario or in scenarios where different individuals within an organization are developing different modules.
Yeah. Okay. We'll move on to the next question. Okay, so actually, Mario, you asked this question. It was, who's actually going to be the person that writes the P4 program? Is it hardware vendors, network system platform vendors, end customers, third parties? Do you guys have any thoughts on who's the target user of P4?
Yeah, I can go with, in my mind, all of these. The main, see, if you see that OEM and ODMs, all of them, some of them will write their P4 program with the switches or the networking gear they are going to sell to their end customers along with it. They may have proprietary features in it. I also believe that in some cases, when you have the white box systems, the customers itself or end customer itself would want to modify that P4, so they may still get a default P4, let's call it, in some sense. They say, I don't need this or I need this, and then they can start evolving. Academia is trying to do the different kind of research. Can I do a different protocol in that? They can try that. So I believe all of them should be doing it. It's just that I think end customers may take a little longer to adopt and modify, but hardware vendors definitely will pick up really quickly.
Yeah, I mean, I completely agree with that. I think to begin with, I think they're roughly aligned in the order in which it'll happen, I guess. I mean, the people closest to the chip will probably start programming it first, because the biggest benefit of this is you don't have to spin a new chip if you need a new feature. I think that benefit seems to be relatively clear, whether you call it configurability or programmability. That sort of seems to already be happening. Whether you expose it all the way to the end user or not might be a function of time and a function of how savvy the end customer is. They may not want to write a program from scratch. They may be happy, as Anurag said, to take a program that's been given and just tweak it in a few ways to maybe just modify table sizes, right? That might be the level of customization they want. But I think the underlying ability to express functionality in code is hugely beneficial from an engineering standpoint for somebody building a chip.
So I think that this is the number of people coding P4 will be comparable with the number of people writing device drivers, right? This becomes part of the plumbing. And my expectation is, especially for mass deployments, if we ever reach that stage where this goes into hyperscale, you might have a few dozen people who write stuff that actually goes and gets into production. Right? And I can envision that the successful brands of P4 programs might become ASICs in themselves that don't have programmable data plane, right? But serve as a proving ground, sort of like FPGAs serve today for ASIC development. I don't really see third parties. If you think about your infrastructure and your network, right, it's unlikely that these will be so uniform that you'll have third parties developing, universal P4 programs to do certain things that are common across deployments, right, at this scale. On the other hand, we have innovation, right, at small scale in labs and so on, so that in that sense, there might be third parties, right, that basically deploy whole systems with their custom P4, whether proprietary or open.
So I'm a little surprised that no one mentioned that what I would think is the obvious answer is that it's going to be the people that attended P4 Developer Day. But
Yes.
Should we get the next? Okay, so this I think is a pretty interesting question. Is that we've been talking about a programmable data plane, a programmable forwarding plane. But what sort of applications should sort of run on a programmable switch versus something that runs on a programmable NIC? And Dejan, you already sort of talked about the need for a programmable NIC. Maybe this.
Right. Well, I'm going to now flip-flop and say that for the most exotic applications that we're looking for, which is embedded deployments, right? We essentially, our NIC becomes a cache controller, essentially. So this vision is that you would disaggregate your main memory across the switch, and then you'd plug your compute into the switch, and the switch shows up as main memory, right? Now, we're not quite there yet today, right? And the performance is going to be pretty bad with the hardware we have, but we're working on that. But I think for most of the more mundane things like disaggregation, acceleration of memory over fabric and replication rate in the switch and so on, a lot of this functionality actually does belong on the NIC, right? We want to launch custom packets, right? So we can't do it with a plain Ethernet MAC, so we need either programmable NIC or other kinds of or FPGA, right, to launch. But yeah, I think the whole point of P4 is programmable switch, so I don't see a programmable switch going away. Otherwise, why not just go back to InfiniBand?
Yeah, it's not switch versus the NIC. We need both. And both will coexist, like Dan is saying. It's not complete without two being there. I mean, people want programmable network, but to do something interesting things, they may want to send a specialized packets or like even you can throw the breadcrumbs that I send a packet which throws the stuff away, launching a state in different parts of the network, and some other guy goes, collects it and says, oh, this path is working. So you can use it as a, like, say, a simple example, part discovery, that is it still alive? Those kind of things. So you can build those things, but a lot of those requires a small logic or towards the server side where the NIC can drive those stuff in P4, and people can write those kind of flexible programs down to the hardware level, data plane level. So I don't see that why versus is a question. It has to be two together.
So I tend to agree we need both, but I wonder, do you think P4 is a language that targets both?
P4 is, the way it evolved was basically for the flexible network, essentially, and NIC is the end point of it in a sense for that network. So I see from the start to the end, it has to be P4. I'm invested in fully.
So, I mean, I would tend to include end-host networking, kernel bypass, things like that into programmable NIC, because as far as I'm concerned, that just looks like a programmable end-host to me, whether it's in the NIC or in the kernel or in user space, is a matter of implementation. I mean, I agree with what Anurag said, which is I think we need both, but I think for a good number of applications, a programmable end host is sufficient. And in some cases, you can't do it in the NIC, in the switch. You might have state that is resident on the end host, and only the end host knows how to actually do that functionality. Like one somewhat application-focused example is something like spam filtering, right? It's only the email server that knows what is spam and what isn't, and so on. It seems hard to like offload that kind of functionality into the network. But I think you will need both. For other functionalities such as measurement, where the problem is deep inside the core of your network, you're really hacking blind if you're like probing from the endpoints. And similar deal for things like scheduling. And you can also get a substantial performance improvement for things like congestion control. Now, as for whether you need a common unified language through all of the network, I mean, to some extent, we're doing fine with C on the end host, C or C++ or whatever you use to program your end host. But there is a benefit to uniformity of having the same domain-specific language that you can use to express your entire network and decouple it from whatever language you use to program the application components of your, basically the application-specific components. So, yeah.
Well, yeah, I mean, I agree with what was said. I mean, probably we need it in both, in fact. It greatly depends on the specific application. I think the one case in which we need it for sure in the switch, in the network, is when whatever we want to do on those packets, we need to do it, we want to do it before they get to the destination. We don't want to take those packets to the destination if we don't need to. So I'm thinking of filtering kind of applications. Then we want to do it in the switch. Doing it in the host is possible, but it's going to waste a lot of resources because we move a lot of traffic to the host. And the other case is, of course, when what we need to do, the processing that we do is related to routing. When we cannot route in the host unless we do some sort of broadcast and select. But again, it's very inefficient. And or certain multicasting mechanism where you want to send to a group of hosts, but you don't want to overdo it. Again, you don't want to send it to too many and then filter. So those are the applications where I think we will need to work with the switches. And otherwise, yeah, it's probably going to be absolutely a combination, or sometimes even interchangeable, like a sort of caching solution. In principle, we can do them in the network, but maybe it doesn't make much sense. It's better to do it in the hosts where we are closer to where they are used.
Yeah, I'm not sure if anyone would really have a comment on this, how to sync P4 state running in a data plane and control plane, but maybe some of the P4 runtime people might have some suggestions on this. So why don't we skip to the next question, and whoever wanted to, I would encourage you to talk to Carmelo and Brian afterwards. It was Samar? Oh, I'm sorry. You were also encouraging. Okay, sorry. Yes, please also talk to Samar. Okay. So maybe this is a good question for Anurag, I think. Is there any possibility to develop a complex P4 program such as DPI functionality that is running on a P4-enabled switch? So clearly you would need to.
Like I said in my introduction, I believe it is possible, but not today, at least not in our Tofino chip as of today. But this is possible. We allow to inspect the packet. Now, the packet, again, it will come to a cost and limitation that probably you can't go all the way to the end of the packet if packet is really big, 1,500 byte or bigger. So I'm not sure if we are thinking about looking up to layer 7, maybe HTTP or things like that. Sure, that should be doable, definitely. Yeah, that's my view.
What? Okay. Well, I don't know if, again, you guys would have answers for this, but when will traffic management become programmable?
Yeah, I could have asked this question.
What's that?
I could have asked this question.
You want?
Yeah, so I can speak to this pain point, right? Ethernet is a really awful protocol, guys, right? So please move to something that's out of this millennium, right? We really want flow control, please.
Means traffic management, sure. It means we as a company are looking into making as a programmable. It's a hard problem essentially. If you see that in terms of 6.4 terabit machine, making decisions every clock cycle in a nanosecond, making everything programmable is a harder problem. Traffic management also requires a lot of very short, very quick control loops. You have to, as an example, if you look at what is the state of the queue and immediately make that decision right away. So in terms of, we are looking those kind of application, how we can enable that to make it more programmable, more extended. So far in our architectures and all of our P4 architectures we have, it's essentially we have ingress pipeline and egress pipeline and traffic manager in the middle of it. So if it is programmable, it should be able to talk to the ingress or the egress pipeline with full flexibility. That's where the more challenges come, that you want to make a decision on this packet, then what happens to the just packet went through. So those are the little nuances, but it is not unthinkable that it won't happen. It is natural progression that once your basic pipelines are all programmable, then the rest of the switch should be. So yeah, I do believe it will be.
Okay, will existing P414 hardware support P416? And I'll just answer yes.
Yes.
It's more of the compiler
Yes.
thing than a hardware change. So, yeah. Okay, so I think this is touching a little bit on a question we already talked about, is what's the right division of labor between networking and applications, between end hosts and switches? A lot of people are looking at offloading computations into the network or SmartNICs or other places. Do you guys have any thoughts of sort of where we draw the line, how we assign functionality? Hey, Mario?
But I guess it's going to depend on the specific application and on the constraints that we have, right? Because on switches we might not have enough memory to do certain things, while we might be able to do it in the host because they see only their own traffic. So I guess depending on the application, we will move that boundary.
Yeah. So I would guess part of your research is trying to push that boundary.
Yeah, so I think this is a very relevant question. Ultimately, once you have a programmable substrate, the immediate inclination is to use it to do like literally everything, right? I think one issue with that is you have to worry about hyper-specializing your network to one application at the cost of degrading performance for others. So as an example, like if you add a key value store into the switch and that takes up most of the memory and it reduces any memory left over for routing, that's not a great design choice from the overall system perspective. And I think, as Mario is saying, in a switch you really have to care about the fact that there are multiple different hosts going through it. So it's not like an end host where you get to use your own memory, do what you want with it. Like all the collateral damage is localized to your end host alone. With a switch, because it's sort of an aggregation point where multiple things go in and out, you have to worry about the fact that, if the memory is all eaten up by something exotic that you're doing for one particular application, it may come at the cost of general forwarding performance or degraded performance for other applications. So it makes a lot of sense, but I think we should look at the costs in addition to the benefits of moving applications into the network.
Yeah, I think Anirudh and these guys are a lot more experienced with this division of labor. I'm more towards the hardware, but from my perspective, network is now becoming natural extension of your compute, essentially. So things will pass and it will be application based, some kind of application which makes sense that where you may use your networking elements as an aggregation point. Like you take multiple packets, maybe you create a new packet out of those and shoots back to the original hosts. So those kind of applications you can do in network where you are actually, so this goes back to the previous question versus programmable NIC as well versus programmable switch. So if you have multiple VMs that can aggregate things in a local switch, local NIC, but anything across the physical servers, you have to go through the switch. And now if you have same P4 program, which does that kind of thing, it's portable. I can make it with some parameter changes to work on NIC versus work on the network. So it is highly application dependent. Most of the heavy lifting will still be done by the host. The networks plays with the packets, and anything which is packet-centric processing probably will start moving into the networks to a degree.
Yeah, so this is all, I agree with everything that's said. I think that I can make a prediction that there'll be a fragmentation here occurring, right, at some point, because initially as there's this bursts of new activity and new research, people always ask for more, and more state, more this, more that. We ran into the first problem, which was the size of the match action element, right, so we want more larger elements and so on. But when successes occur, then people start asking for less because you find out that you're using 90% of your silicon is dark, right? Because you don't actually have anything to populate those elements if you're doing a simple protocol. So I've seen this happen in a lot of ASIC projects, right, where you want the smallest FPGA that fits something if you're going to sell it as an FPGA, or you make an ASIC that is just the right size, right, for the amount of compute you do. So in that sense, there's no single answer to that question, right? It'll heavily depend on the application, right?
Okay. So I think maybe we have time for one last question. I guess people are asking for differences between P4 and OpenFlow. They seem to be, sort of targeting different purposes. I don't know.
Yeah, they're orthogonal, sort of.
Yeah. So I think, like Mario said, they're sort of orthogonal. OpenFlow is really targeted at control plane programming, whereas P4 is targeting at data plane programming. So maybe we should try. I think we kind of covered this one already. Yeah. Okay, so this is probably a good one to end on, is do you guys think there's a path to incremental deployment? So could a network with 10% programmable and 90% fixed function switches still provide partial benefits?
Well, yeah, again, it depends on the application, right? Yeah. There are going to be applications where if you have a couple of switches that can do something special to the traffic, you already get a benefit, or you get the full benefit because you don't need to do it everywhere. There are others where you need to have it in every single switch. So, I don't know, if you think of something like ECN we were talking about today, I think it's somewhere in the middle, right? It's best if you have it everywhere, but if you have it at least in a few switches, if those get congested, you get a benefit from those. If one of the other, whatever, 10% or 90% that is not supporting it gets congested, then you have no benefit. But also, it's not harmful to have it. So, yeah, again, it depends on the application, I believe.
Yeah, I think I was the one who asked that question. But as far as, at least my interest in this question has been mostly around congestion control protocols like XCP and RCP. One of the reasons they didn't really take off was because, they work if there's a single bottleneck, that's the only place that's going to get congested. You just turn on ECN or more exotic scribbling in the packets on the switches. But the moment you have multiple bottlenecks, it's not clear what the behavior of the protocol is going to be. Like, best case, it probably doesn't hurt. Worst case, it does something weird and unpredictable, right? And I don't think this is something we study enough as researchers, which is like, how do we get from where we are now to where we want to be? And I think congestion control is one example where I don't necessarily think there's a great story for incremental deployment unless you clearly know that this is exactly where congestion will happen. But other functionalities could be slightly more forgiving, like measurement. Maybe you can just instrument a few switches to collect statistics. It's a completely passive functionality. So I think, my personal take on this is it's a question we need to think about, because otherwise we might, it might end before it even starts, because you don't know of a way to get benefits from having 1 or 2 or 3 switches before upgrading your entire network to of 10,000 switches to P4.
Yes, in my mind, this is a valid question. I think that will be the natural progression. That network is some components of the network will be replaced by flexible, and then the new deployments will eventually pick up more and more and more as more people feel comfortable about things being programmable, and they also find the ways to use that programmability to their advantage. It is one thing to be programmable, and another thing is to actually use the advantage of it. You can be programmable. If you are still using exactly the same way as some other fixed function devices are, then you are not doing justice to it, or not taking full advantage of it. So like Anirudh says, some of the applications I see is that you may throw these devices in different parts of the network just as a monitoring or detection devices, or anomaly identification, or some interesting cases that these things showed up, or why things suddenly shows up in this path, which shouldn't have ever. In those kind of anomaly detections definitely is one thing. Homogeneous things definitely helps. If everything is same programmable, it's much easier to reason about in the system. It's also it's easy to do different types of protocols or different research where at least you're sure that everybody is behaving the same way. It's almost like a 10% autonomous car on the road. That gives you full benefit. No, it's a lot more difficult problem to deal with. But yes, it's the same thing. Few people buying it, more people will buy it. So it's going to be that way.
Yeah, I think the answer is yes. Also, if you just from one example that comes to mind, right? Let's say you're building a data storage system for a cold storage, cold data. Maybe you just need the ports, right? So you might have 3 switches do all your paxos that you need for your storage application, but you just need the ports for capacity. You don't need more bandwidth, right? So in that case, you'd probably buy the cheapest hardware to get more ports and have enough compute.
Okay, so I think we're out of time now for the panel session. I'd like to thank Mario, Anirudh, Anurag, and Dayon. And thank you for the conversation and your opinions.
Thanks for that.
Okay, so that pretty much wraps up our program today. I just wanted to end with a few quick remarks. For me, I think it's a very exciting time to be in networking. Many of the fundamental abstractions that we've taken for granted over the years are being rethought, some for the first time in many years, at all levels: hardware, software architectures, low-level programming languages, high-level APIs, and applications. And all of these efforts are being driven, I think, by real-world problems with buy-in from key stakeholders from across industry. So I think it's a very exciting time for P4. If you guys want to stay involved, some next steps are, of course, all the software for the exercises that you have today are available on GitHub at open source P4 Lang. And I'd encourage you, if you develop new applications, to contribute them, give back to the community. And also, if you're interested in becoming a p4.org member, membership is free and open to everyone. Join the mailing lists, join the working groups, and contribute ideas and codes. So thank you very much for attending today. I hope you learned a lot, and there's a small reception outside.